Okay, so one of the first things that I'm actually going to need you guys to be able to, I don't know, do, like I'm going to give you a worksheet to work on in a little while. Actually, I think I already gave you a worksheet. That's a big package of stuff yesterday. Is being able to recognize how neutrons, electrons, and protons will work within atoms and ions. I think I probably wrote atoms. Oh my goodness, I can't spell it. Atoms are neutral, and ions are charged. Did I write something like that maybe yesterday? The basic idea being that if it's an atom, the number of protons is guaranteed to equal the number of electrons, always. But if it's an ion, well, that's actually very useful for other things. But ions, protons, and electrons don't equal each other. Because of that fact, actually, ions can then stick together and form compounds. And that's where we're trying to go to today, is when we can actually make a sodium ion combined with a chlorine ion, and they stick together to form sodium chloride. And that's very useful. Otherwise, we'd only have 114 things in the universe, and that's all we'd have. If all we had were atoms, that would be very boring. Does that make sense? But because of ions, because electrons can be gained or lost, things can actually stick together. So, do you guys know about the energy levels of valence things? Maybe if I go to the slide here, Lab maybe did diagrams with this with you guys, showing how things have different electrons in orbits. Okay. So maybe I'll gloss over that a bit, but basically the idea is that there's supposed to be something called an octet rule. Do I have that written somewhere here? Maybe this slide. Whatever. We'll go to this slide here and we'll write it in if we need to. So valence electrons are the outside electrons, and normally we want 8 of them. There's something called an octet rule. We want 8 electrons in like the outermost level. And the reason why, sorry that's so messy. The reason why it's normally 8 electrons, pardon me here, is that usually you get 1, 2, 3, 4, 5, 6, 7, 8 electrons in like a row. Does that make sense? There's actually some exceptions though. For example, helium only wants 2. Now, even if you get further down the periodic table, even in this row right here, these electrons in the middle here, these are called transition elements, they actually function a little bit differently. And so really, even though there's something in this row, it's actually 1, 2, 3, 4, 5, 6, 7, 8 electrons. Almost everything wants to obtain 8 electrons. And if it can do that, it's considered to be kind of stable. Okay? Which is why everything in the last column, helium, neon, argon, you guys heard this before? They're called the noble gases, or sometimes inert gases, because they don't react. They are stable. What else should we talk about here? Let's just go to the example sheet here. Let's see if we can do this. I'm sure you guys know this. You're giving me nods, so. Do you guys know what it means if I say carbon-13? Have you heard of the term isotopes? Okay, an isotope refers to how many protons, neutrons, and electrons something has, basically. And that can differ depending on situations. So, for example, carbon. What is carbon's atomic number always? Guaranteed. Yeah, I mean, it has to be. And that atomic number is actually based on the fact that it has 6 protons. If it has 6 protons, it's carbon. Guaranteed. Does that make sense? The 13 then refers to how many total things it has in its nucleus. And so that's the protons and neutrons. So if this 13 right here, it tells you how much atomic weight it has. Now I gotta point something out. You know that number that's like 12.01 or 22.99, the one with the decimal places? We're gonna talk about those later. Those are different than this, which is kind of confusing. The reason why is that technically one individual atom is either a 12 or a 13. However, if you have like a whole bunch of them, there's going to be some 12s and some 13s and some 14s. And the number on your periodic table is like the average of all of those. Does that make sense? So like give me one sec, would you? An individual carbon atom could have 6 protons and 7 neutrons. Anybody know how I got this 7? 6 plus 7 adds to 13, right? An individual carbon atom could have 13 total things in its nucleus. Another one could have 12, another one could have 11. That number of 12.01 then is like the average number that it's going to be. And we'll use that number later. Go ahead.
Do we ever have to like figure that number out, or is it always like just...
I'll have to tell you something to figure it out, because you wouldn't know otherwise. Yeah, I'll give you some information to solve it. Like the sodium 25 number. If I tell you it's sodium 25, you should be able to figure out how many protons and neutrons it has. Or if I don't give you the name here, using the rest of this info, you should be able to work backwards. Does that answer your question? Okay. So like say sodium 25. Sodium has to be number 11. Otherwise, it's not sodium. And if I tell you an individual atom of this stuff weighs 25, then there must be 25 total protons plus neutrons. So there has to be 11 protons, because again, otherwise it's not sodium. So then by default, it has to have 14 neutrons, because 14 and 11 makes 25. You guys are good on that? Okay, let me try one more row. You guys do the last two then. So atomic number 14 then gives away its identity. Number 14 on the table is silicon. Now, we don't know which version of silicon it is. For sure, silicon has 14 protons, but it could have 14 neutrons, 15 neutrons, 16 neutrons. We don't know how many neutrons it has. I kind of like to think of neutrons in my mind. I think of it as it makes the molecule fatter. It doesn't actually change the molecule. Like it's not, if you add an extra neutron, silicon doesn't become phosphorus. It just makes it a heavier molecule, but it's still the same thing. Does that make sense? So you can have as many neutrons as you want. So there's got to be 14. These two columns will always be the same. So then this better be 15. An individual silicon atom could have 15 neutrons, but it could have 16 or 14 or 12 or 17, and I don't know how many they have. But on average, silicon weighs 28.0855. Does that make sense? Well, try the last two rows, if you haven't already. See if you guys get the concept. I guess I should have written 29 right here. By the way, if I didn't mention to you guys yesterday, feel free to make all sorts of markings all in these data booklets you have here. Anything you write on the data booklet, you can bring, like, these are what you bring into a test or something. So if you need to put extra markings on there to remind you what the noble gases are, or basically it's a cheat sheet. So 19 and 24 should add up on this guy here to be 43, hopefully. Is that right? Atomic number still has to be 19 because it has 19 protons. So I just need to figure out who number 19 is. It looks like it's potassium.
Oh, right.
Does that make sense?
So the number of protons and the number of neutrons have to equal the atomic weight.
Exactly. Yeah. Protons and neutrons are fairly heavy things, and so they contribute to weight. Electrons are actually very light, so it doesn't matter how many electrons something has, they're really irrelevant to how heavy something is. It's kind of like if you were to have 43 elephants, and then you were to put a bird on top. Like, well, does the bird make it a little bit heavier? Yeah, I guess, but like, you have 43 elephants. Who cares, right? Does that make sense? It's like that same scope. So, although there will be electrons in these atoms, the electrons really don't contribute anything worthwhile to mass. So for the last one, with it being a 64, that guarantees that it is, 64 is down there, gadolinium. That's cool. Gadolinium 64. So it has 64 protons. So its atomic weight, add those two up. Just don't screw up math, Chris. 143. We're good? Cool. You guys have done this before? Awesome. Moving on. Okay, let's talk about ions then. Okay. Everything we just did there was an atom, but sometimes things gain and lose their electrons. Now, it won't change their mass all that much, because like I just said, electrons are fairly weightless in comparison. Okay. But if they do so, if you gain electrons or lose electrons, you're no longer an atom, you're now an ion. And the way we can tell things are ions is because there's going to be a little charge up in the corner there. So like this one right here is a potassium ion. Whereas this one right here is a chlorine atom. Does that make sense? But now we have a chlorine ion. So the way ions work is if it's negative, it's picked up more electrons. If it's positive, you can't actually pick up more protons. Okay? Because if you picked up more protons, you would change the type of matter you were. For example, like potassium can't have an extra proton because then it wouldn't be potassium, it would be calcium. So how do you get a positive then? Do you guys know? You lose an electron, yeah. So let's walk through a couple here. Potassium is atomic number 19. Hopefully you can just look that up, which means it has to have 19 protons. So these two columns will be the same as each other. If it is positive, what happened to its electrons? It lost one to get down to 18, which means it has a charge of +1. 18 is very common. 18 is because the first orbital had 2 electrons, the next one had 8, so 2 plus 8 is 10, and the next one also has 8. So 2 plus 8 plus 8 actually gives you 18, and 18 is a very stable number of electrons. So now it's no longer an atom, it's an ion, and when we do our next set of notes after this, if 2 ions form, it makes a compound. Does that make sense? Okay, let me do one more, then you guys can try the rest. This one right here is a chlorine atom. The reason I know it is an atom is I did not put a little symbol up here in the corner. So that means chlorine is atomic number 17. Hopefully you can just look that up. By default, it has to have 17 protons. And if it is an atom, it will also have 17 electrons, so it does not have a charge. So if you get the concept, try the rest. Yesterday I probably mentioned, I think I did, the idea that chemistry is kind of like learning a new language. And this is, to some degree, kind of like learning your letters. Well, like my daughter's 3. One of the things I'm working with her in flashcards is like, here's a letter, tell me what it is, right? And to some degree, that's kind of what I'm asking you to do here. I don't want you just to memorize the periodic table, but I need you to know how these letters work, right? So chlorine, what does a chlorine negative really mean on like a deeper level? And one thing that I'm going to start stressing you guys with, and we might even do like, say, some mad minute type drills, is I need it to happen quickly. Because this is one of those things where if you really want to be fluent in a language, you can't always be going back to your periodic table. Oh, where the heck is chlorine? Okay, how did the electron, you know what I mean? It needs to be one of those things where if you actually want to be able to read chemistry and eventually be able to write it and speak it and know what's happening, it needs to happen quick. So I don't mean to rush you guys, but I also don't want to take forever on it. So hopefully you've tried most of these. Let me just fill in some answers and hopefully you guys have the same thing as me. 11 should be sodium. 11, that would be a +1. Plus there. Selenium, 34. 34, that means you need 36 for -2. If you put like 2 minus, I don't really care how you wrote it. It doesn't make a difference to me. And then nickel is 28. And it should be 28s across the board because there's no symbol. Does that work? Awesome. Okay. I gave you guys yesterday a whole slackload of stuff. One of them should have been like a workbook. Yeah, like I said, Science 10, review, something along those lines. I'm going to very often give you guys worksheets. They're not due, ever. That's not the point. The point is that if you need practice, here's practice. If you don't need practice, I'm a firm believer that do something else. I like sports analogies, so hopefully they resonate with some of you guys at least. I used to be a big fan of hockey, still am a little bit. Vancouver Canucks being my team. Do you guys know who Ryan Kessler is? Yeah. Recognize the name? He used to be one of my favorite players, then he moved to I don't like him anymore. But I heard a story once about Ryan Kessler. It was the year before he scored 40 goals for the Canucks. Kessler always used to be a very good skater, great penalty killer, but he wasn't very good at shooting. And so all summer, he practiced, I don't know where, like I imagine in a garage or something, right? And they said he shot hundreds of pucks a day. He didn't work on his skating. He didn't work on his shot blocking or whatever else. He worked on his wrist shot because he knew that his wrist shot was his weakness. And the next year, he scored 40 goals. I mean, granted, he played with the Sedins for most of the year, but like, it obviously paid off. And I like that in relation to school because my philosophy is don't work on the stuff you're good at. I think that's a bad idea. I think sometimes kids like to work on things that make them feel good. And so you go find a nice, easy worksheet and go, I feel really good about myself. But how does that help you? Does that make sense? And so when I give you guys stuff to work on, that booklet's not due. I'm not going to mark it. But if you want me to, I'll totally go over it with you. Work on something like that if this doesn't make sense to you. Does that make sense? If you get it, go do something else. Make sense? Oh. Okay. I talked about ions. Probably don't need to do much on this slide here. You guys know the term for positive ions or cations? You guys have heard that before? And then the negative one is anions. If you ever forget, I don't know whether he came up with this himself, but I always tell you it was Cody Van Driesken who taught me that cats have paws. So therefore, cations are positive. I don't know whether he thought of that himself, but I tell every class that, so I always credit him because it wasn't me. So cations are positive, cats have paws. Anions are negative. That'll do. Okay, let me show you an example of some questions that I might ask you on a test, and then we're going to take a bit of a break. I'm a big believer that you can't sit still for an hour and a half in class, so I'm going to give you guys a 5-minute break to go wander around and do stuff. But I want to show you an example of, this would be an example of a question I might give you on a test. Okay. Have you guys done numeric response questions before? And how those work? Yeah. Okay, so basically it's filling in the blanks with numbers here. So like manganese 52 would have blank protons and blank neutrons. So how would I figure out its protons? I gotta look for manganese on the periodic table. No, that's magnesium. Yeah, manganese is 25. So if it has 25 protons, but it adds up to 52, then it better have 27 neutrons. Does that make sense? That might be a question that I'd ask you on a test. Or Mn2 plus would have blank electrons, while Mn4 plus would have blank electrons. It is possible for things to have different numbers of charges. So how many protons does manganese normally have? 25. So if it's going to have a 2 plus, it would only have 23 electrons. Does that make sense? Because then 25 protons and 23 electrons means there's 2 extra positives. So then if it's an Mn4 plus, it better be down to 21 electrons. I'm getting a lot of nods. So. All right, one last question then here. Selenium has blank total electrons. So selenium is right here. How many total electrons does it have? I didn't say it was an ion, so if it's number 34, it should have 34. That makes sense? How many valence electrons does it have? In terms of valence electrons, then you start counting from the side here. So you go 1, 2. Don't count these guys right here. I could teach you all of them. I don't think I could teach you. There are whole courses on how funky these guys right here are. Because you see how they have like more than one charge? Everything in the transition state, there's some weird chemistry to it. We kind of, at lower levels, we kind of ignore it. So 1, 2, 3, 4, 5, 6 valence electrons. That's how many selenium they have. Does that make sense? All right, cool. Go take about a 5-minute break. Come back when that clock says 22. So feel free to go out, use the washroom. All I ask is, like, don't bug other classes. Don't get yelled at by their teachers. Okay, but go take a break, stretch your legs, grab something to drink or eat. And then when you come back, we'll talk about how to name things. So we'll do the nomenclature section. So now the goal is, let's say we take ions and we put them together and we make compounds out of them. I need you guys to be able to either take a formula and give me a name for it, or if I give you a name, give me a formula. one of the first questions I might ask them is, why is this so important? And scientists, I would say science develops slowly over time in various different places in the world, but it's very important that we all speak a common language. So that if I talk about NABR, some scientist in Russia also knows what NABR is. Does that make sense? Like, it's important to have a universal language. So often I have my students see whether they can name any of these ones here. Do you guys want to give it a try for like 5 minutes here? I don't mean to take a ton of time. Basically, like, if you know its name right away, write it down. And if you don't, then move on. So, see how many of these things you can either name or write out.
So this is aluminum trioxide. Yeah. Aluminum 2, because that would be the second. Turn on
Yeah.
Compounds and like the numbers, you don't have to put like diatribe and it's less molecular, but do you do like cesium 2 chloride?
We only do Roman numerals if there's more than one recognized possibility. And so as a general rule of thumb, we're going to use your data booklet here. Like say cesium right here only has a +1.
Okay.
So don't worry about putting that in chart. But let's say it was chromium. So chromium has a 3 or a 2. Then we would have to put down a 1.
Yeah, I remember that.
So
That makes sense?
So none of these will have.
Yeah.
Lead will. Lead actually has 2 valence states of 2 and 4.
Okay, but then how do we know which one is yours?
Great question. Okay, so then you actually have to figure that out based on the opposite thing it combines with. So it combines with 4 chlorines, and each chlorine is usually -1. But the only way that's going to fit is if lead is the 4 version.
Okay, so then so we put lead 4?
Yeah, you use like the Roman numerals.
Yeah, I do, but as a too small.
Fair enough.
Okay.
Thanks for doing that.
Okay, stop where you're at. I don't want to be mean, so you get this in a little while here, but I want to challenge you. One of the things I need you guys to be able to do is do this quickly. That's what's going to be this next 2 weeks. That's one of the reasons why I want to do this chemistry, is because if you want to be fluent in chemistry, I get that, I mean, it's day 2, right? It's going to take you a little while to get into the swing of things, but at some point I need you guys to be able to look at this like I do, and be able to look at it and say, that's cesium chloride. That's aluminum oxide. That's lead 4 chloride. And like literally be able to look at it and be like, I know that instantly. Does that make sense? I know you're not there yet, and that's kind of why I've scheduled some work time, because kids always need that. Okay? So what I'd like to do here is I'm just going to read off the names right now just verbally, and feel free to write them down if you want. And then I want to go over how to name them in case you've forgotten. But this needs to be something you need to have in the back of your mind, that if you want to be good at chemistry, chemistry is not just naming stuff. Chemistry is knowing the names and then actually doing something with it. Does that make sense? So here's the answers in case you want to write them down. Cesium chloride, aluminum oxide, The next one requires a Roman numeral. It is lead 4 chloride. We'll talk about Roman numeral stuff in case you don't remember. The next one is gold 3 nitride. And then E, I heard a couple of you guys, you picked up on how to solve that one. It's a molecular covalent compound, so you call it trinitrogen pentaphosphide. F is chromium 3 nitride. And G is dichlorine tetrabromide. So hopefully at some point, fairly soon, you can do what I do and just look at it and go, I know that word. And if you like that reading analogy, like my daughter can see her letters. I mean, at some point, I'm going to want her to be able to look at a word, C-A-T, and be able to say, oh, it's cat. Right? And I mean, at first, you got to spell it out and go, cat. You know, does that make sense, though? Okay, so here's the last ones. NaBr is sodium bromide. PbF2, lead 2 fluoride. Ooh, this one's challenging. It'll be Li3P. H2O. Cu2O. N4I10. CON. AlCl3. And Ca3N2. Like I said, hopefully at some point, what I just did there is you. Okay, I don't know, maybe that sounds kind of mean, but that point needs to be in 2 weeks. Okay, so it gives you something to work on though, right? That's why I said if that first stuff we just did before the break, if you can handle that, fantastic. If you can't, work on that, right? But over the next little while, this is your next goal then. Be fluent in naming things. Fair enough? Okay, so let's say though that you was like, holy smokes, where did you get some of that stuff? I have some notes on this, okay? What I might recommend if you are kind of struggling with this at first, I have a flow chart I've made to try to help figure out how to name things. And so you may want to write this down in your data booklet, like your formula booklet there if you want. If you need it, it's fine. But here's kind of a flow chart as to how you might try to figure out how to solve things. I'd say if you're given a compound, first question is how do you know that it's a compound? Well, there's more than one thing in it. Does that make sense? If it's just Cu, that's a copper atom. If it's Cu2+, that's a copper ion. But as soon as you see something like CuO, okay, now we need an element. Now we need a compound naming scheme. Okay? So first thing you got to do is figure out, is it covalent or molecular? Like those words are used interchangeably. Or is it ionic? You guys know the difference between the two? What makes something ionic? Perfect, that'll work. Yeah, it's actually, I'm going to do this a lot in chemistry. We often tell you like partial truths when you're first learning things. That's actually not the official definition of ionics. We'll get to that later in the course. But for what you need right now, if it's a metal and a non-metal on opposite sides of the table, that'll work. Okay. Whereas covalent stuff, these are all anions. They should all be like negative charged things. And if you put multiples of those together, you can make it molecular. And then ionic things, I think you can break them into 3 categories. There's the binary things, where there's just 2 things. There's multivalent things, which require this Roman numeral. And then polyatomics are on your table, like this open space there. There's often like a chart of things called polyatomic. So let's walk through the 4 possibilities here. Kind of jog your memory. So first thing, ionics are metals and nonmetals. You guys seem to know this, so let's fast forward. Here's how you name it. The cation always goes first. So whatever is the positive thing, put it first. Don't change its name. General convention is you don't use a capital letter, but I'm not going to dock you marks if you had like a capital S here. But general convention is unless it starts a sentence, we don't actually put that capital there. The second thing, the anion, we just change the suffix to "ide." Okay. There's a few of the chemicals where it's kind of tricky to figure out how to say it. The main ones that are tricky are sulfur. Sulfur becomes sulfide. Phosphorus becomes phosphide. Not like phosphoride or something like that. Selenium becomes selenide. Those are usually the 3 hardest ones. Phosphorus is phosphide. Sulfur is sulfide. And selenium is selenide. But change the ending to ID. Does that make sense? Cool. Okay. I've got some examples here. One of the trickiest thing is knowing how to use the ratio of cations to anions. And I have some manipulants here on the board that hopefully can help if you're stuck on that. Like, let's say I give you sodium chloride here. Sodium is a +1 charge. How do you know that sodium's a +1 charge? Does it know the answer to how you know it's a +1 charge? Okay, your data booklet will tell you, like it says in there, sodium is +1. Okay. That being said, there is actually not everything is listed. Chlorine is a -1, but your data booklet doesn't tell you that. Okay. You guys know how to figure out some charges if it's not listed, especially for these guys over here. The charge of everything that's a noble gas is 0. So sometimes what I recommend kids do is maybe just right above the last column. All of these things in this column here, they all have a charge of 0. They're all full of valence electrons. They don't want any more. The next column over is called the halogens. Anybody know what its charge is? Yeah. The reason why is all of these things right here have 7 valence electrons. And if they could get 1 more valence electron, they would then be full as well. If they gain an extra valence electron, though, then they would be negative. So everything in this column is -1. Everything in this column then is -2. Everything in this column is -3. Does that make sense? So your data booklets don't list every single charge out there. There's another problem with your data booklet. If you look at like the big periodic table, it's way more in depth. Technically, like chlorine could be a -1, a +1, a +2, a +5, +7. So like, it's kind of tricky because you're not going to have all that information in your data booklet. But if you look at the big periodic table, sometimes there is more on there than this book necessarily has. But as a general rule of thumb, 0s, -1s, -2s, -3s. Does that make sense? Actually, it's the opposite on the other side over here. These guys are +1, +2, +3, as you go along. However, then you get to this middle section here. These are the transition elements, and they have, like I said, I don't even know that I could give you a lesson on it in like less than a day and a half. So if you don't mind, just ignore transition metals and just whatever is written in your book, those are what's possible. So like, you know, +2, +3. So back to here then. Yeah. All over the place. If you have a chlorine and a so here a sodium and a chlorine, and one is a -1 and one is a +1. You just need one of each. Does that make sense? But if you have aluminum chloride, aluminum being a +3, it has a different charge. So being a +3 charge, you're going to need 1, 2, 3 negatives to make it fit. Does that help visualize how charges work at all? So that's why the formula is AlCl with a small 3, because you need 3 chlorines to make it fit. And then one last one here. Where is it? Calcium. Oh, hard time with these today. And nitrogen. Calcium is a +2. How do I know that? Because it literally tells you in your data booklet. Nitrogen is a -3. It probably doesn't say what nitrogen's charge is, does it? In your data booklet, does it say?
No.
Okay, so then you just need to know it's in the 3rd column over. So in order to make this work then, let's see. You see how like a 1-to-1 ratio won't work? But if you like double up the calcium, it also doesn't work. So you need to kind of do like a 3 against 2 kind of concept. Does that make sense as a visual? So you're going to need 3 calciums, so Ca with a small 3, nitrogen with a 2. You probably learned a crossover method at some point, but I think lab always teaches this. Did you guys learn to do something like this where if you find calcium's charge is a +2 and nitrogen's charge is a -3, you put like the 3 there and the 2 there? You guys learn that? Okay, so if you get that concept, you're good. The only thing I'd ask if you do that, erase that mess up there then, because these things are no longer charged, they're together as a compound. Works? Awesome. Okay, moving on. There are some things that are multivalent. Usually they're found in that transition element section. Like I said, there's different stuff going on in the orbitals there, but basically there's more than one charge possible. And because of that, we always have to write a Roman numeral down here. So you sometimes have to work backwards to figure out which of the 2 possibilities it is. It could be like, say, a 2 or a 3. So like, for example, if I gave you Cr2s3, sulfur, I guarantee you it's a -2 because that's just the column that sulfur falls in. So then kind of working backwards, if you have 3 things at -2, you have a total of like 6 negatives. So then you better have 6 positives. But if you need 2 of them, then like the only way this will work is if it's the 3. So therefore we choose the chromium 3 ion, which means I totally goofed that up, didn't I? Because if it's supposed to be the chromium 3 plus, it's my mistake. That should have been a 3. Does that make sense? I'm going a little faster, but I'm gathering you guys seem to recognize this. Okay. If you don't, find me later, right? Because that's what I have work done for. So, third possibility, it could be polyatomic. And these are things like the NH4s or the OH minuses. And I said earlier, they usually get found in that top little hole in the periodic table. Not that they go there, it's just there's a nice spot there. So usually they put a box there with like stuff. Makes sense? So you just need to know how to name them. The only one on there that is positive is ammonium. The rest of them are all negative, and so they're also ionic. You just name them as you see them. So like MgSO4 is called magnesium, and SO4 is called sulfate, so you just call it magnesium sulfate. These guys are usually easy to pick out because there's more than 2 things there. There's 1, 2, 3 different things. Have you guys ever heard much about how these polyatomic things work? Has Lab talked about that at all? It basically like it exists as though it's like, yes, there are like 4 different things here, but really it exists just as a single structure. And this whole thing right here has like a positive charge. So although yes, there are smaller bits to it, it basically functions as a unit. And so they call it a polyatomic. Yeah.
Why don't we have to put ions here?
We don't want to change the names of some of them because the ides already exist as a name for the just basic this one and this one ones. Because if you change it to ide, then you know how you have like a sulfate? If you change it to sulfide, sulfide is already something else. Does that make sense? So just if it's one of these guys, just name it as you see it. So barium carbonate is Ba and carbonate is CO3. This guy's +2, this guy's -2. Do I need to actually like cross over the 2's if they're like exactly even to each other? Sound good? Okay. I've got some examples here, but you guys can probably look those if you want. Here's an important one to note. Sometimes you might need to put a big bracket around a polyatomic. Like calcium is a +2 and nitrate is a -1. So we put a big bracket around the whole nitrate and then put the 2 afterwards. What you don't want to do is this, CaNO32. Because that means you have 1 calcium, 1 nitrogen, and 32 oxygens, and that is not what we're looking for. Does that make sense? So make sure you catch the bracket around anything you have to double if there's like a polyatomic. Do you guys have this slide in your notes? Okay. How about I give you a reasonable amount of time to actually try this one then? So 5 minutes. See what you can do this in 5 minutes. If you can't, don't worry. I mean, like I said, my goal is to stress you and challenge you. So see if you can get these 10 in 5 minutes.
Well, what is IUPAC?
Oh, sorry. IUPAC is just like the naming system that we're learning.
Okay.
It stands for like International Union something something chemistry.
Okay.
It like that's what we're doing. We're doing IUPAC naming. Good question. Okay, let's go over these at 5 after. See how many you can get. Fire away.
So when you use the system of like dry dye and stuff, is that when it's metal or non-metal?
That's actually what we have. The one thing I haven't covered yet in notes. The die try is when it's just only these guys right here.
Yeah.
So there shouldn't be any of those on this slide yet because we're going to cover that. That's my next slide is doing the
Oh,
coloring
yeah.
ones next
I
year.
just wanted to. So it's more fun, right?
Feel free to ask anytime, okay? Yeah, what's up?
PO3, what's that?
Oh, you know what? I haven't covered that yet. Okay, so there are some rules for things that are very similar. So you have a PO4 right there?
Yeah.
PO3 is going to be phosphate. And it changes the suffix IT. I have that in a set of notes. I think we're doing it tomorrow. I didn't realize I threw one of those in here now. The way it works is that, if it has a per and then an 8, it's the highest of how it works for oxygens. Now if it's just a regular old H, it's down 1 for oxygen. If 8 turns into ite, it's down another 1 for oxygen. And then hypo and ite is the lowest.
Okay.
In this example, it was 4, 3, 2, 1. But that's not a guarantee. Because like this one here, the phosphate is actually the 4.
Yeah.
So that means the per phosphate would actually be PO5. And the phosphite would be a PO4, PO3. Does that make sense?
Yeah.
One last thought, the charge never changes, by the way.
Okay.
So if it was a -3 charge and then you bump it down to an ite, it still is a -3 charge. Yeah, that works. Good question.
It's 2. No, the 2 goes towards CRP2. Yeah. Oh, it's in
Well, let me give you one more minute here. I know you're not going to finish. Just so you guys know, I know you're not going to finish. That is the point.
E2.
Okay? Like I said, I feel like it's my job to challenge you. And so I'm not going to give you enough time to finish them all. Maybe you will, actually. But so take one more minute, finish what you can. One thing I like to do, and if you guys are up for it, we can do that. I like to do mad minutes with chemistry. You guys ever do those back in like math? Or, like you get a big paper and you try to see how many you can get. But like one of the reasons why I like those is because it's designed so that you won't finish. That is the point, you know. And then the challenge is how many better can you do than the previous day, right? So that day 1 you get 20 right, and the next day you get 25 right. But like, the point behind it is that I don't expect you to finish them all. So. Yeah, what's up? Fire away. What's up? Can I name them there? It isn't. It's phosphite. I mentioned it. Those guys are there. Guys, when you do the PO3 one, it's not on your table. We're going to talk about that tomorrow. PO3 is phosphite with an ITE. Sorry, I put that on there when we probably shouldn't have. Hey, let's talk through these then. See how you did. Like I said, I'm hoping that eventually you'll be able to just look at them and go, I know it. Right? So sodium fluoride. Ooh, does cobalt have a charge? Sometimes you might have to look up and see if there's a charge. Cobalt 2 selenide, yttrium sulfide, tungsten. Do you guys have charges for tungsten in your data booklet? Tungsten technically has a whole bunch of charges. Okay, yeah, tungsten 6. You know how you don't use Roman numerals if there's more than one charge though? Tungsten actually has like a whole crop of charges if you look at a big periodic table. So you might want to put the Roman numeral after tungsten, but if you didn't, I wouldn't mark you wrong. But it's tungsten 6 iodide. Silver nitrate, and that's actually manganese. More than one charge? Yep. That would be manganese 4 phosphite. If I talked to you already, I screwed up. You shouldn't have had to do a phosphite. We'll talk about that another day. Let's see. Chromium phosphide would be Cr3p2. Cr3p2. Ammonium oxide would be NH4. All of that would be in a big bracket. Then you put a 2. Then you'd have an O afterwards. Calcium nitride would be Ca3N2. Vanadium chloride would be VClO3. And then that's ClO3. Nope, ClO2. It would be V, and then your ClO2. That thing would be in brackets, followed by a 5. Copper would be CuAt, is acetone. And nickel 3 acetate would be Ni, and then the acetate is kind of a really long, complicated thing. So it'd be Ni, then you'd open a big bracket, you'd have CH3COO, you'd close that bracket, and then you'd have a 3. How'd you guys do? Okay. And again, my goal here is that eventually become fluent. If you got all 10, fantastic. You will have a reasonable amount of time when we begin. One of the things I always stress to my students, though, is that if you really do want to go on in chemistry to especially the 30 level, you can't be spending all of your time searching your periodic table looking for stuff. Does that make sense? No. So, I mean, do I have to look once in a while still, too? Sure, I might not know whether manganese has different charges. No? So, I mean, hopefully that's just a quick look. Okay, last thing, then I'll stop talking for the day. We should talk about how to name molecular stuff or covalent stuff. Honestly, this is the easiest of everything. All you do is you put mono, di, tri, tetra prefixes in front of things, just based on how many there are. You have to pick these out, though, because everything is going to be anions. They're all the nonmetals. Oh, one more thought here. These guys share electrons. Do you guys notice the difference between the two? Ionic things have like a give and take electron relationship. An ionic thing that is a positive and a negative, one of them literally gives away their electron. Whereas these covalent things, they all collectively pool their electrons together. I have an analogy I like to use, so I can do it right. I want to buy something that's $10. And I have $8 and you have $2. No, that's a poor example. Change it up here. I want to buy something that's $10. You want to buy something that's $10. I have $8, you have $12. So how do I make this work? Well, you give me 2 extra of your dollars, so now my 8 becomes 10, your 12 becomes 10, and we can both buy something. Does that make sense? That's ionic. That's a give and take relationship. Covalent would have been what I started by saying. I have $2, you have $8. Do either of us have enough to get to 10 on our own? No. So we're going to pool our resources, share, and so now we have to share what we've purchased. Does that make sense? So yeah, naming these things is very straightforward. You need a prefix, and then again, you change the ending to I. What I might recommend then is if you don't have these prefixes memorized, one really clever student once showed me, you know how there's all these numbers at the very, very top here on your periodic table, listing the rows there? Write the prefix underneath them. So like make 1 mono, 2 is di, 3 is tri, 4 is tetra. You write them all up there. That way, if you forget them, you have them written down. While you do that, that's kind of one of my last slides, isn't it? I just have some examples on here. So you guys can look through those examples. Hydrogen's kind of a tricky one. If you have to end with a hydrogen, call it a hydride. Kind of sounds funky. Here's where it is. Here, let me give you a second to finish writing that down, and then I'll talk about these polyatomics. This was that thing that I was talking with you and you about there, about the ite. I put that in before we talked about it in slides. Give me a second though. In the polyatomic section, sometimes they don't list all of them because there's like a naming scheme that you can use to figure those out. And it's based on eights and ites and how those work. And maybe you remember this, maybe you don't. So here's the basic idea here. It's a reference point is the 8. It might have 3 oxygens. It might have 2 oxygens. It might have 1 oxygen. It might have 4 oxygens. I don't really care how many oxygens it has. But whatever 8 is, whatever it ends in 8, that's the reference point. If it has 1 more oxygen, it becomes a per something 8. Like say per chlorate, per bromate, per phosphate. Does that make sense? So the highest of all the oxygen is a per 8. Then there's just the regular old 8. Then after that, there's ite is one below that. And the one below that is something called a hypoite. And so the way I recall these ones, if I ever forget, is that there's one family of them that's all listed. It's perchlorate, chlorate, chlorate, chlorite, and hypochlorite. And it's all in the bottom little corner right here. I should probably do a few examples of this. I don't think I have a lot in here. Let's say you have an SO4. SO4 is listed for you. It's called sulfate. Does that make sense? What if I gave you then SO5 2 minus? What would you call it then? Exactly, yeah, you'd call it a per sulfate, just because it has 1 more. If you had SO2 2 minus or SO3 2 minus. By the way, as the oxygen number changes, the charge doesn't. This guy would then be known as a sulfite and a hyposulfite. The names for like eights and ites and hypos and pers are not based on the oxygens. It's based on where they are in reference to each other. So in this particular family, 5 is the highest down to 2 being the lowest. But if I were to give you like this particular family of BRO3, BRO2, BRO, and BRO4, these are the families of like this one is bromate, this one is bromite, this one is hypobromite, and this one is perbromate. So don't worry about the pers and the eights and stuff based on the oxygens, just based on how they're referenced to each other. So there are a few extra polyatomics that you could be asked to know about that aren't actually in this top section here. Is that something you guys covered last year? Is that like ring a bell? Okay. It doesn't come up a lot, right? But it does come up occasionally. So I might recommend write something like this then down somewhere on your data sheet. Like that's why you have this whole big booklet, right? You can write whatever you want in there. I think this is my last slide, right? Second last slide? I don't know. Okay, so one other thing you might want to write down, there are a few common chemicals that we just give like a common name to. Like you guys all have heard of H2O being called water. Technically it's dihydrogen monoxide, but we don't call it that, we call it water. Does that make sense? So there will be a few compounds here and there that are compounds that we don't name it according to its like special name, we just call it water. So I would recommend these are the main 5 that you should know, and we'll learn more as we cover chemistry. Does that work? Cool. Okay, practice time. So I've talked to you guys now for the last day and a half. So we've got, I don't know, 25 minutes left today, and all of tomorrow. Hey, I want to make the rest of that time now your time. I want to give you some time to work on things. So I don't know, do you guys have these next 2 slides in your notes or not? Or is that where it stops? Okay, so why don't I try this here? One of the best ways to practice is just to give you a whole crap load of things to work on. Here, if you want to maybe take like a snapshot with your phone or something like that, are 56? Yeah. practice things, both for naming to like formula to name and name to formula. This is not do or anything like that, but it's just practice. Okay? And if you still want more than that, I have another booklet here as well. That literally is just pages upon pages of practice. Okay? My philosophy truly is, if you get it, go home. I'm serious about that. If you are good on this, you can go, so long as I have that. Okay? If you want practice, though, this to me is the most important time because I can go around and work with you guys. So, like, please feel free to call me over and ask for help because I will work with you as much as you need. But like the next day and a half is now for you. Does that work? Cool. Okay. Let me know how I can help. I pretty much almost say this at the end of every day. It's now your job to ask me how I can help you.